All right, thanks a lot. Thanks for having me. It's a pleasure to be here. My name is Patrick Eugster, and I'm a full professor at the Università della Svizzera Italiana. That's how we call it, USI here in Lugano, Switzerland. I have a couple of my co-authors here with me today, so I brought my posse in case I need backup for any pesky detailed technical questions. Yeah, let me dive right into the talk then. So, I mean, I'm preaching to the choir here. We've witnessed this, what I call the rise of the trusted execution environment. We've seen after over a decade of work using just plain software solutions that these are not good enough for protecting data that's in use. And so it's a natural and necessary evolution to see this hardware support coming up, and it's very welcome. Yeah, again, we've kind of failed with software only, and this has been shown recently through a study of data breaches showing that a large number of data breaches are connected or involve data that is in the cloud. So that's definitely alarming, and it shows we haven't been able to do enough here. So yeah, I think needless to say, we can all agree standard encryption is good for data in transit and data at rest, but not data in use. And it's great also to see all these different platforms, these different options, starting, of course, with Intel SGX, the original, but then AMD following up, ARM, CCA, TrustZone, AWS, rolling its own, Intel doubling down with a new platform, and recently NVIDIA with first kind of trusted GPU. Yeah, so it gives us a great number of options to choose from, which is great. But having a lot of options can also be problematic because that brings you to the question, which one do you choose or which ones? I'm going to elaborate on that shortly. Before I do so, though, I'm probably going to get killed for this, but I do it over and over again. Still, I think we're sometimes a little bit too quick at dismissing software solutions. So, homomorphic encryption, there's some nice works out there that are practical, that are useful. And the reason also why I'm saying software in general is that we have to face it. I mean, we need software in any case, or at least the context that we're coming from, which is distributed data processing in an untrusted environment like the cloud. It's great to have these TEEs, these fortresses on individual nodes that can protect the data in use. But if we're doing distributed computations, then we still have to pass data back and forth between them. So what connects these things is software. And we still have to do things such as establishing keys and so on. So we have still a number of software crypto solutions that we're using anyway, or that we need to use anyway, at least at the present. There's also other advantages to software-based solutions. I mean, they're easy to inspect. I can look at the code. I know what it's doing. I can't say as much for a hardware platform, sorry to say. Of course, I don't get something like remote attestation immediately with software. So I don't know for sure that that's the software that's actually then running. But if that's the case, and if I can control the deployment, then software is relatively easy to deploy. Worst case, I rewrite it in a different programming language or adapt it to some libraries, and usually it runs. So there's some advantages definitely on the software side. And also, as I'll show shortly, in some scenarios, it can be actually competitive on the side of performance still. So again, there's a number of different hardware solutions, and again, by no means I don't want to dismiss this. Quite the contrary, we rely on these heavily, so it's great to have them. But yeah, there's substantial differences between them, and I'm sure you're all familiar with these. I mean, it starts with the basic features and functionalities, how to use them, the APIs, what are the exact features that they provide. There was a nice paper that gave some overview of these features and how they differ. And then, of course, the exact guarantees that we're getting, by and large, confidentiality of data and integrity and confidentiality of computation. But yeah, there's some fine grain, there's some fine print. And also rarely are these guarantees really, really precisely defined. So it's also just very difficult to compare them to begin with. And then along with these, there's known attacks for all of these TEEs. And again, this is not to diminish them or their contributions or pit them one against the other, but it's just a fact that there's no bulletproof solution. And so this still, doesn't really help in choosing any one particular solution. And then the other thing that I mentioned, which is efficiency or performance. So coming from the use case of data analytics that I'll elaborate on a little bit more shortly, we ran many very simple micro benchmarks. Here I'm showing some using a number of well-known data processing operations, SQL style, filtering, selection, projection, so those kinds of things. And originally we wanted to just get an idea of how the different trusted execution environments fare. But again, the goal here is not to say this one is better than that other. And then in the mix, we also threw in some partially homomorphic encryption to see how that performs. And we're actually quite surprised originally to realize that homomorphic encryption can be quite fast. As you see here, we have these 9 different operators, and we have latency for these micro queries running in logarithmic scale on the Y scale, and the green parts are essentially the homomorphic encryption ones. And so you can see if you look just at these green bars compared to the other 3 respective bars next to them for each of these operators, that on average, and this is averaging over, I don't remember, 100 runs or something, on average, they're actually faster. But having said that, and the explanation for that, for those who may wonder, is relatively simple, is that, again, we're in this perspective of distributed computation. So data comes in over the network, and it's encrypted. It has to be encrypted. In this case, we're using AES GCM. So it first has to be decrypted in an enclave. Then it can be processed on. Then it has to be encrypted to be sent out to the next node, where the same thing then happens. Whereas if you're using partially homomorphic encryption or homomorphic encryption, then your data is already encrypted, and assuming it is the right encryption that supports, of course, the operation that's being performed, which is the case here, otherwise we couldn't report it, then you just get your data and you perform your operation and you're done, and you send it off, and there's no decryption or encryption, and that explains the difference. However, of course, things are much more complicated. Look at them in more detail. And so if you see the mauve or purple parts that we added here, that is the decryption time at the end of say a query. So if you're not just looking at individual operations, but you're running a query which consists in several such operations and stages, you're lining them up, then the last one, you have to decrypt your result for the user, right? And if you're using something like homomorphic encryption, then a lot of these schemes are very expensive on the decryption side. And so once you add that, then in fact, in many cases, trusted execution environments become more efficient, right? But that would be for typically this last operation, right? So you really have to have a closer look at what is it that you're doing with what kind of data also to understand just plain performance-wise, and just in this case, say, focusing on what they would have as a common denominator in terms of guarantees, which is confidentiality of the data, which one you would want to prefer just from that plain performance side. Of course, again, the guarantees would also have to be taken into account, right? And then the other side of things, at least as far as I know currently, there's no single trusted execution environment product that is deployed in all the 3 major clouds at this point in time. Amazon has its Nitro, Azure, SGX, and SCV, I believe, and same thing for Google Cloud Platform. But so if I, as an individual, want to write a piece of software already, I have to ask myself the question, in which Google or in which cloud do I want to run this software? And so that just leads to this big problem, at least for us, for me as an academic, how to choose, which one to choose of these trusted execution environments, because guarantee-wise, they're definitely stronger than these software alternatives. And also how to reconcile. Now, if I want to build a system that can run in different clouds, or maybe even, God forbid, at some point, start some query in an edge data center using one of these TEEs, and then move the data after pre-filtering and pre-processing into a cloud data center using another mechanism, so needing some kind of interoperability. How would I even reconcile the guarantees that I'm getting from these different possibilities that I have, these different mechanisms, if I want to combine them or put them together somehow? And yeah, that's without even considering the software solutions and other accelerators like trusted GPUs that are now on the market. So yeah, how to address all these questions? So at this point, we decided to not panic. Let's take a step back and really figure out what are the requirements that we have. And so this maybe gives a little bit more of perspective. How do we even arrive at this point? So this is an overview of work that we've done over the years, and it's actually great to see some of the co-authors among the audience here. Some Purdue alumni. I used to be a professor at Purdue for about a decade. So I would claim my group was the first to really look at generic data analytics using a scalable distributed backend. So originally this was MapReduce. That was a while ago. Of course, the thing is outdated. And so then we moved on to other systems, Spark, which I'll touch upon a little bit more shortly, and then also stream processing in the context of the Apache Storm system, and so on. Right. But so while we're doing this work and also in hindsight, reflecting on that work, we were trying to come up with what are requirements that we have here. And so we came up with this fourfold requirement. We dubbed this the site requirements. And the first one is obvious. It's security. We want strong security. But for us, it became quickly apparent that also a little bit looking at industrial solutions, that talk is cheap and everything is claimed to be secure this, secure that. So really one has to be looking at the detail. And once one does that, then I think it becomes clear that formally defined guarantees that are formally verified become of interest here, at least to us from the academic perspective. The second requirement, which comes out from this difficulty of choosing is this: we want to be independent from any specific platform. At least as an academic, I can't just hire another team of 10 developers to port my systems to the next hardware platform that comes out. So that we want to be as independent as possible from any security mechanism. We want to be transparent, again, from the perspective of a data processing system, like a data analytics system. I think it's pretty clear that the end user is typically not an expert programmer. And if they're good at programming, then probably not an expert in security. So, they shouldn't at every query have to reason about security constraints. That should be taken care of by someone who's an expert and kind of once and for all, or at least not at the level of every single query. And then finally, of course, performance is key here. If we come up with solutions that have, I don't know, say still 10 times slowdown over the same execution without any security guarantees, unfortunately, still a lot of users are rather going to put the money in the piggy bank in case there is a data breach, which costs them something, and in the meantime, just save money and not spend as much money running their stuff in the cloud using fewer instances, fewer cycles, and so on. And I think these may be trivial to everyone, these requirements, but I don't remember seeing a lot of works where they explicitly put them down, and also really just reflecting on, can we achieve all four of them? And it's pretty obvious that a subset can be achieved quite easily. We have plenty of demonstrations of that, systems that exist in academia and out there in the industrial world, but really getting all four to the fullest extent is a really daunting task. And so this is where I come back to the title of the talk. Though this is our approach, we believe that formal programming techniques can really help bring these four together and cover the all four of these together. And I've been urged to not become too formal, and so I'm going to try to stick to these few Greek letters or symbols that you see here, and not have too many or many more of those. I hope I didn't miss any while editing the slides, but I'm happy to bring some more Greek letters later if someone has questions about these things. So concretely, what does this mean? How did we combine these requirements? So let's illustrate that through a piece of work that we presented a year ago at PLDI, or a little bit more, which is the system called Hydra, which is a confidentiality preserving data analytics system for large-scale deployment in the cloud built on Apache Spark. So how does it address security? What we provide is a confidentiality guarantee that's based on non-interference, which is a very well-known and in the meantime, old concept that's been used widely in programming languages to reason about confidentiality in detail, also in the meantime for integrity. Concretely, this is enforced by a static information flow type system. So before a query starts being executed, it is verified for this guarantee. And if that doesn't hold, it's not executing, right? So plain and simple. How do we address this independence, platform independence requirement? We're using a also relatively established or well-known, old, I would even say, multi-level security policy. So customizable, you have different levels of confidentiality, which are arranged according to a lattice. But we extend that with a mapping of these mechanisms or of these levels to security mechanisms. And I'll illustrate all of these in detail shortly. So it's a relatively, I would say, pragmatic means of really involving the user, saying, what do you prefer? What do you want? And it's to some extent of taking responsibility. All of this is then based on or uses a formal query language, which is a mix of Lambda calculus. Lambdas are widespread currently or these days in programming languages, so it's not that fancy anymore. And a mix with relational algebra. So we have relations that are the basic abstraction on which we perform queries, and then security annotations or abstractions. How do we achieve this transparency? Well, what happens is that users will express their queries in a subset of this language, which doesn't have any of the security annotations or abstractions. And then our system will automatically transform that. So fill in the security annotations based on the security policy that I mentioned earlier. And we've proven this transformation process to preserve semantics. And again, all of this will be illustrated shortly through some concrete examples. And then finally, once we have a formal language that allows us to reason about security in detail, in this case, confidentiality, we can also use it to reason about performance. And as far as this transformation goes, it sounds a little bit spooky. What's the magic there? We actually also open this up to the user, or at least to an advanced, experienced user, in that we have a notion of pluggable heuristics that really can then decide which mechanism to use where. And we have a domain-specific language that really makes it easy to express these heuristics. And again, I'll show examples of these in a few slides. So this is roughly the workflow of our system. The bottom left, the data analyst would write their query. In our prototype based on Spark, this would be in Spark SQL, unmodified Spark SQL. And then the query would be transformed here using the security policy that I mentioned, which would be the duty of a security expert to express. And of course, over time, it can change. Then the data schema would be annotated by the data owner or the data manager, probably together with a security expert, to decide which data is at which confidentiality level. And then finally, the security expert, with what we may call a performance engineer, someone who understands the performance side of things, would write or choose a heuristic that would then drive the transformation, which then leads to this annotated query with all the security annotations that is then compiled and optimized. And as part of that, it's verified against for this guarantee that we want to provide before it's then executed. So this is the only part here, the executor, that would happen in an untrusted environment like the cloud or data center, an edge data center, or both. We also, in some cases, rely on some limited resources back on the side of the data analyst or the user. So we may use some trusted on-premise computing resources in some rare case, but the rest of it would exploit something like SGX or whatever is available based on the security policy that then drove the transformation. And that would happen then automatically, right? So at the point here, final execution plan, the query is transformed, all the code is added to use these security mechanisms to bridge the gap between the different nodes, make sure stuff stays encrypted at all time, and so on. And then the result finally to the bottom right, that would then go back to the left to the data analyst. So simple security policy. I mean, we all have seen these in classes, in textbooks, relatively straightforward. Here, a simple example of multi-level security policy with 3 levels: public data, let's say low secret data and high secret data. And then here, the second step, this mapping that I mentioned, which assigns the security mechanisms to the levels of this policy. So here, for instance, we will be saying Data that is at the level high secret can be operated on or used in the client domain without being encrypted, or it can be used and operated on within SGX without being also or further encrypted. Or for data at the low level, we allow the cloud to operate on that data as long as it is encrypted, or to use that data as long as it encrypted with any of these encryption schemes, right? And then finally, as I mentioned here, the data is annotated with the labels, relatively straightforward. These are two tables taken from the TPCH benchmark, which we're going to use then later for evaluation. So here the data owner would just add these labels, low, high, etc. And then these security annotations, or the security part here, would just be inferred automatically based on the security policy and based for a given query and the given heuristic that is going to be transforming the query. So it's not really part of the data schema. Right. So here's a high level some example of a query that's being transformed. This is in our formal core language, so I could show you an example. I should have probably put that, which is in concrete Spark SQL syntax. It's really fairly close, but we don't have to go through it in detail. Suffice to say, at a high level, we're aggregating some stuff that's coming out of a filter, where previously we created we joined two relations. One was this table customers, and one was this other table orders that you saw on the previous slide after some filtering, right? So this would be a plain vanilla query expressed by the user, and then all this stuff here, these annotations, this part would be running in SGX. Here we're using AES GCM for encryption. Encryption and decryption as needed would be all inserted automatically when the query is transformed. A little bit more in detail, how does the system then work? I mean, it's nice to declare at a high level which mechanism to use, but then how does the part really get deployed using that mechanism? So we have a rich library here that allows us to declare or to write, say, plugins for different mechanisms. So for trusted execution environments, for instance, they can be inserted as native trusted execution environments. So that's kind of the case of what we have with SGX, where we wrote a custom interpreter that we're running because we can't just drop an entire virtual machine in there as easily. But for more recent platforms, there's that possibility. So the user could write here, this is a Scala trait, could implement this trait. Kind of, you can think of it as a wrapper to really encompass the code that it takes to then deploy something from the analytics platform inside such an instance, right? And then similarly for the encryption schemes, we have different traits that one can implement to use to wrap existing encryption schemes. And then on the heuristic side, similarly, we have a relatively rich API to describe these heuristics. These are kind of just the basic types. And I apologize here, there's this term Scilla, or this name that pops up. That's really just the follow-up of the Hydra work. So it is the kind of the next version of the system. So we're really talking about the same thing here, but because I took these code snippets from actual code, we have the new names in there in some places. But yeah, much simpler. I mentioned it earlier, we have a domain-specific language for describing these transformation heuristics, and without going into too much detail, here the one to the right, that was the original heuristic that we used in Hydra, which mixes partially homomorphic encryption schemes together with SGX in a relatively simple way. If you remember those micro benchmarks where we determined that certain operators are faster using this or that, so that's essentially what we're using here. For every operation that's performed as part of a query, we just look at essentially a table that we have from those micro benchmarks, which just says which mechanism is expected to be faster for that operation, and then that one is chosen, with one simple exception to the rule, which is that, as you remember, if you have this partially homomorphic encryption-based operation at the end, you have potentially an expensive decryption to pay. So we avoid that scenario by just saying we start typically off with partially homomorphic encryption, but once, for instance, we have a limitation of what the encryption scheme can do in terms of the operation, once we switch over to SGX for the remainder of the query or for the next stage, we never ever go back to homomorphic encryption, right? So it's kind of a one-way street. And then, in fact, we have this much simpler heuristic here at the top left, which is really just flipping back and forth. Whatever is just locally for that given operation that's being considered expected to be faster, that's the one that we're going to use, right? And again, this heuristic is applied before the query is run, right? So it's not something that we do currently dynamically. We could introduce some dynamic checks and decide on the fly, but currently this is all static. So the implementation, I mentioned already, our system is built on Apache Spark. It's used through the original Spark SQL API. We leverage the Catalyst extensible query optimizer. And in the meantime, so these numbers here on the lines of code that we modified are pretty outdated. For the new version that I mentioned of the system called Scilla, we've gone in and done some much deeper changes, much more substantial changes, in particular to the runtime system, to be able to really enforce security at all these interactions between nodes. So these are not really up to date anymore. The current status, we've tested and evaluated this in 3 major clouds, AWS, Azure, and Google Cloud Platform. We currently support I'd say we really support 3 hardware mechanisms. We support SGX, SEV, and Nitro. We're working on TDX. I wouldn't say it's really mature yet. In terms of an academic prototype, it's mature, but you know what that means. And then we currently have these 6 partially homomorphic encryption schemes that we support, and we're working on integrating 2 more of our own, which we designed, which are symmetric, of course, then providing weaker guarantees, but very, very improved performance. So let's look at some results here. So I mentioned already the TPC benchmark, which is a standard benchmark in the data analytics space. And we chose also so that we can compare to 2, which at the time were the state-of-the-art systems, which also were evaluated using those benchmarks. The first one being Cuttlefish, which was our own system, which was using partially homomorphic encryption inside Spark, so that it's a fair comparison. And exceptionally could be configured to exceptionally use SGX for overcoming limitations of partially homomorphic encryption. So essentially re-encrypting the data. But in this case, we have this fallback also, which we're also using with Hydra, of going back to the client side and re-encrypting data there. And the other system we're comparing against is Opaque, or at least an early version. Probably you're all familiar with that. And we're comparing against those systems using our system, but in either case, we're just using the mechanisms that the corresponding system also supports. So in case of Cuttlefish, that's homomorphic encryption. In case of Opaque, it's SGX. And the goal here was really just to see, are we kind of competitive, right? Because we have a much more generic system. There may be levels of indirection, and we were actually happy to see that, no, that's not the case. We can actually keep up with these. We have substantial speed ups over Opaque, but I'm sure their system has improved in the meantime. They were using different libraries for SGX than we were using, and so on. So, but again, that was not the goal really. It was just to see, can we keep up? The more interesting part for us was this Hydra hybrid version. So here, I mentioned this earlier, simple heuristic. We just said, okay, what if we now try to mix it up between SGX and partially homomorphic encryption? And here we're able to show significant improvements over our same system, but in each case using just one of these mechanisms or classes of mechanisms without the other. So that was kind of encouraging for us. Like, yeah, there may be a scenario where you want to mix in software for performance purposes. Here's some later numbers yet from this new prototype or new system version that I mentioned, Scilla. So here we were first and foremost interested in how do the different trusted execution environments compare against each other in our system. So definitely a disclaimer here, right? This is the way we use them in our system. I already mentioned SGX has an interpreter inside in our case. The others we're deploying containers in them. So it's definitely different levels of abstraction, which will have different impact or have impact on the performance, also on trusted compute base. So all with a grain of salt, right? And then, yeah, how do you compare a node that has support for SCV against a node that has support for SGX? So we tried to find comparable, let's say, specifications, but yeah, the goal was not to say this one is faster than the other. But you can see that in our case, at least, the SGX version is significantly faster. But again, that is because the code is running that we're running in there is really customized, heavily customized, and it only contains what we need in there. So that makes substantial difference. The other two, it's kind of a wash between SCV and Nitro, right? Yeah, and the difference to SGX is also due to this encryption and decryption when entering and exiting enclaves, that in the case of SCV and Nitro is taking place in Java. It's implemented in Java. In the case of SGX, we're running the C code. So definitely improving there. And we could probably improve things on the other platforms as well, using the Java native interface, for instance. And then this most interesting part for us was this heuristic. And so here we took these two heuristics that I showed earlier, these two slightly different ones, because we're interested in how much difference does that make. And so we were comparing what we call SGX plus PHE star, which was the a little bit lengthier heuristic, if you remember, a little bit more complex one, to the much simpler one, which we call SGX plus PHE. And in fact, it turns out that latter one, the simpler one, is significantly faster on average than the more complex one. The reason being that, again, how much that additional overhead for decryption in the case of homomorphic encryption weighs in depends on which operations you're looking at. So there were still a good number of operations where, despite that decryption overhead, which we also have with a trusted execution environment, the homomorphic encryption version was still faster. So this kind of much simpler heuristic of just looking locally at every operation and then deciding where to deploy that or which mechanism to use to secure that was performing better. And if you remember roughly the size of that heuristic was like 10 lines in our domain-specific language. So very simple, very easy to write at least basic heuristics there and modify them. All right, so I hope I convinced you of the approach in general. There's a lot more work to be done. We're looking into mechanizing the proofs of our guarantees. The same way it's easy to say that something is secure. It's easy to write a paper with some proof that something is secure. Is it really secure? So here the goal is to take to the next level, use interactive theorem proving to really verify the framework. Of course, you don't know whether the theorem proof is correct, but I think the bar is being increased, and that is the goal. We're continuously looking at new mechanisms that we can add to our system and support in there. We're looking at a number of extensions, generalizations, refinements. Of course, we want to add integrity guarantees. We want to do differential privacy because that's the thing these days. And it's really, it makes a lot of sense in practice. We're also looking at alternate data flow models or systems. So data analytics, Spark style is an interesting thing, but there's others. In our case, for instance, we're considering all data belongs to one party. So what happens if we're combining data from different users? What's happening if we're looking at something like more real-time online processing, stream processing rather than batch processing? So these are all things that we're looking at coming from, again, this simple perspective of try to use formal programming techniques to bring these things together. All right. I'd be happy to take any questions that you may have or delegate to my happy helpers that are online with me.
That was a great talk, and formal methods are certainly on the upswing, and I see sort of required in more and more places now. So it's great to see this work here. As with the previous talk, feel free to pop off of mute. We're not terribly formal about this, and ask questions. One thought that came to mind is we rely on attestation to know that we're interacting with the thing that we think we're interacting with. Can you draw a connection for me between the verification that you do here and remote attestation?
The two are at least so far not connected. So the verification that we do is really, at least in the system that I present, or systems, it's really based on confidentiality of data, and we're kind of trusting the deployment environment to deploy the right thing. Yeah, understandably, obviously there's guarantees that we get with trusted execution environments that we don't get with software-based mechanisms. Having said that, we've done in the past in my group work on software-based remote attestation for wireless networks, using things like time-slotted communication, so where you can get really synchrony or timeout guarantees, so you can really bound the time that someone could, say, compute a hash to hide up their traces or hide the fact that it's a different piece of software that's being deployed. And I think some of that could be applicable here, but it's definitely, I'm going out on a limb here. We haven't done the research yet. But yes, we are limited in terms of the guarantees that we are providing.
Okay, thank you.
I'm kind of curious. You mentioned really early in your paper that you're comfortable with published open source software because you can review the software and kind of see what it's doing. And you called out that's just not possible with hardware, but I kind of wanted to challenge that assumption a little bit. Do you believe that it might be possible? And I know this is kind of underneath the layer that this paper was presented at, but since you presented it, I wanted to challenge it a little bit. Do you believe it's possible to review hardware designs in a way that's similar to the way that one reviews open source software and reason about the confidentiality guarantees that are implemented in the hardware?
For sure, but I think then the problem becomes similar to attestation, right? Then if you give me a particular chip, right, do I know that that one actually is according to the specification? I know that there's been some works going in that direction also, but admittedly, I'm not an expert here, so I wouldn't know. But I know that I cannot kind of pry open a chip and then see, okay, is this pin connected to that one ever or not? Yeah.
Right. And I think that's gets back to what Dan was just talking about, attestation, and that's a completely separate parallel topic.
Yeah.
So I'll leave that there. But super interesting paper. Thanks for this. And obviously formal proofs are very much needed in this field.
Thank you. And
Yeah,
again,
definitely.
I mean, I understand my limitations on the side of hardware. So I am coming from this from kind of an application side, and I'm happy for all feedback that I can get from the hardware side on this.
It's the exact same problem. I mean, what you said, how do I look at a bunch of code if I'm a hardware designer? How do I look at a bunch of lines of code? And you mentioned, thousands of lines of code and reason about whether or not it's providing any security guarantees. It's the same thing when you look at a tape out for a, FPGA. It's the exact same thing.
Okay, and with that, we have time for maybe one quick question, if there's another one.
Yeah, probably
I saw somebody
two
coming up
talks is
with
a little
me.
bit taxing for people. I'm happy to take questions at any point. Just shoot me an email, of course, if something comes up later.
Okay, great. Thanks again to Professor Eugster and your students who joined you, and the colleagues. It's great to have the talk today.
Thanks a lot. Great being here.